From the outside, building an emulator might seem like an enormously complex project, and in some cases it definitely is, but the foundations and the principles are far from impossible to understand. Over 15 videos and more than a year of work, we've been building a 16-bit virtual machine from scratch. You'll find a link to the full playlist of videos in the description. We've covered numerous sweeping topics such as the basis of computation, the design of an instruction set architecture, stacks, interrupts, memory mapping and banking, as well as creating a parser and an assembler for the VM's architecture. And now we're finally going to put everything we've built to use by creating a fantasy game console. So what exactly is a fantasy game console? In short, you can think of it as an emulator for an imaginary retro game console, with the CPU and its surrounding mechanics of the virtual machine at its heart. We're going to build out a system very much like the NES or the Game Boy, where games can be created in the LLJSVM assembly language and played in the browser. The graphics will be simple, and the memory and execution speed will be constrained. These constraints let us get a feeling for what it must have been like to be a software developer in days gone by, and building the whole system will serve as a valuable model for how emulator projects really work, highlighting considerations and trade-offs that go into designing real computer systems beyond the CPU. So now that we know what we're aiming for, let's talk about some of the details of the system. Arguably the most important aspect of any game console is what kind of graphics it can produce. Our fantasy game console is going to have a 240 by 112 pixel display. The screen will be divided up into 420 8x8 tiles, and each pixel on a given tile can be one of 16 colors. A color table will map all the values of a nibble, half a byte, to a color that the system can draw. Since an 8x8 tile has 64 pixels, and we need 4 bits per pixel to describe the color, a single tile can then be described in 32 bytes. The virtual machine has a 16-bit wide address bus, so the address space ranges from 0000 all the way up to FFFF, 65,536 bytes. The tile data for any given game is mapped to a region of memory descriptively called tile memory. A total of 256 tiles can be mapped, meaning that tile memory is 8,192 bytes or 8 kilobytes. The memory is mapped starting at address 0 all the way up until 1FFF. After tile memory comes the interrupt vector, a table of addresses that the CPU uses to orchestrate the flow of execution when interrupted by external devices. It holds 16 addresses and thus takes up 32 bytes. Next is the sprite table. The sprite table is 512 bytes wide and contains enough space to describe 32 sprites. A sprite is a 16-byte data structure that describes a tile-based object, which can be drawn arbitrarily to the screen. Sprites are used to display all non-background or foreground objects in a game, and generally move around the screen and are usually interactable in some way. In Super Mario World, for example, Mario is a sprite, as is Yoshi, the enemy that gets eaten, the dragon coin, and almost everything else that isn't static. Sprites have an X position, a 16-bit value measured in pixels, and a Y position, also a 16-bit value measured in pixels. They have a tile index, which is a 1-byte offset into tile memory. There is also an animation index, and this is added to the tile index every frame to figure out which tile should be drawn. You might wonder why there are 2 indexes that seem to do the same thing, and the answer is that with this system, the programmer can lay out tiles in such a way that animations are sequential. So the tile index can point to the start of an animation, and the animation index can point to the exact frame. Sprites also contain a byte for the blend mode, which controls how this sprite's pixels interact with the sprites and the background pixels beneath it. Then there are 9 bytes that can be used to store arbitrary data associated with this sprite. The game programmer can decide what these bytes mean and what they should be used for, but common scenarios might be flags for collision, hitbox size, information about what kind of object this is, and whether it's part of a larger structure made of several sprites, and so on. Next, starting at address 2220 is background memory. This is a 512-byte region that stores an index for every one of the tiles that make up the background. You might notice that 512 is quite a few more tiles than the 420 tiles that I mentioned in the beginning. That's because there are 2 extra rows and columns of tiles that appear off screen and won't be drawn. The entire background layer can be scrolled by writing to special memory mapped registers that control the background offsets in the X and Y directions. Likewise, at address 2420, there is a region for foreground memory, also 512 bytes with corresponding memory mapped registers for a scroll offset. This means that the background and foreground can be independently scrolled in both directions at the same time. Directly after foreground memory is an 8-byte region that contains the mapped input values. The Fantasy console allows for 8 buttons to be mapped. The directions up, down, left and right, the 2 main interaction buttons A and B, and 2 secondary interaction buttons, start and select. And although it's not optimal in terms of space, for simplicity's sake, each button is given its own byte. When the button is pressed, the value at the corresponding memory address will be a 1, otherwise it will be a 0. The value of the button is latched when the frame is drawn to the screen, and is stable for the entirety of the next frame. To keep the alignment clean, the next 8 bytes have no special function, and can be used by the programmer for anything. Next, we have the global flags and registers. This is a 64-byte section that holds memory-mapped control registers, such as the previously mentioned background and foreground offsets. Other registers in this region control things like the foreground blend mode, bank switching if it's configured, and DMA transfers, which allow the programmer to copy or otherwise manipulate large chunks of memory in a single operation. Much of this space doesn't currently have a function, but it can later be used to expand the system's capabilities. Finally, from address 2670 onwards, the player is free to load game data and code, about 54 kilobytes worth. However, since the stack starts at the very end of memory and grows upwards, the full amount cannot really be used in practice. A question you might be asking yourself is how an individual game could be loaded into this memory space. In retro consoles, games came on cartridges. Inside a cartridge there would be real hardware like ROM, RAM, or even persistent storage like SRAM hooked up to its own battery so that progress in a game could be saved. As a side note, some games even contained specialized hardware able to augment the console. The Super FX chip is a famous example of this. Its job was to facilitate the creation of 3D polygons that could be placed directly into the frame buffer, but it also allowed for more advanced sprite manipulation, as seen in Super Mario World 2. Of course, when games from systems like the SNES are played in an emulator, a ROM format is used, which describes the hardware capabilities and data that these cartridges had. Let's try to put all of that into perspective. From a systems point of view, we're going to have a few things, some of which we've already built during the course of the 16-bit VM series. First, at the heart of the system is the CPU. Then we have a memory-mapped address and data bus, attached to which will be tile memory set up to be read-only. Then we'll also have background and foreground memory, the sprite table, the global flags and registers, and main memory, which will hold the game code, data, stack, and interrupt vector, as well as acting as a general working memory region. Perhaps most importantly though, we'll have a graphics pipeline, with first-class access to the memory mapping unit. That pipeline will be responsible for pulling graphics data from tile memory and using it to combine data from the sprite table, background and foreground layers into a set of pixels that can be rendered to the screen. And of course, there will be some kind of game controller input, memory mapped to a specific address region. For the rest of this video, let's build out the basis of what is the most important component, the graphics pipeline. To get concrete, this system is going to be running in the browser, and the canvas element is going to be acting as our screen. In the source code folder, I've added a skeleton index.html file with a canvas element and a script pointing to an empty file called fantasy.js. In order to properly see this page, we need to serve it with a web server. You can use whatever you want for this, but I'll keep it simple and use the simple HTTP server module that comes with Python 2. If we navigate to localhost 8000 in the web browser, we'll see our canvas element with its black border. The first thing we can do is to define an array of the 16 colors that this machine can display. They are somewhat arbitrarily chosen for now and will probably change in the future. If anyone actually has suggestions for a palette, please let me know in the comments. These colors are defined as RGBA values, and the first color is just full transparency. Next, we can note down the constants that define the size of the screen. It's 30 tiles wide by 14 tiles high, and there are 8 bytes per pixel row and column in each tile. The width of the screen then is tile width multiplied by pixels per tile, and the height is tile height multiplied by pixels per tile. If we find our canvas element with document.getElementById, we can set its width and height properties to what we've just calculated. Checking in with the browser, we can now see that the canvas has been resized to 240 by 112 pixels. Now, the problem is that a 240 by 112 pixel display is actually very tiny on a modern system, and it would be nice to be able to scale this up somehow. To remedy this, we can add a scale factor variable to our code and use it to calculate the width and height variables. If we choose 6, for example, the canvas will now be 6 times larger than it was before. This also means that when we come to draw pixels, we need to actually draw squares of scale factor times scale factor pixels instead. In order to be able to draw to the canvas, we need a context object, which we can get by calling getContext with the 2D argument on the canvas element. To set the fill color we'll be using while drawing, we need to assign a string to the context.fillStyle property. This string can be any valid CSS color string, and since our colors are defined in the RGBA format, we'll use the RGBA function syntax. To draw a rectangle to the screen, we can call the fillRect method. It takes an X and a Y position on the canvas, as well as a width and a height to draw. If we use the position 64, 64 with a width and a height of 1, we will see a single red pixel at the top left-hand corner of the canvas. If we multiply the height and the width by our scaling factor, we'll draw what a pixel really looks like in our system. It's still pretty small, but it's at least visible. Lastly, we can use a value of 8 pixels instead, and we'll see the size of a single tile. Now we have all the essential elements we need to build our display. Let's start with adding some helper functions. First, we can add a color function, which will take one of the colors we've defined in our table. We can destructure the R, G, B, and A values and set the fill style accordingly. Next, we can create a drawPixel function, which will take an X, a Y, and a color C. We can call color with C and then fillRect. X and Y both need to be multiplied by the scale factor, and the width and the height themselves are just scale factor. We can test this out by writing a nested for loop for every pixel in our display. For the color, we'll combine the X and the Y values in an interesting way to look up a color in the table. The AND with hex F here ensures that our number is never larger than 15, which is the last index in our color table. After drawing all the pixels with our function, we can see this cool rainbow road-like pattern being drawn to the screen. Great, everything is working just as expected. The fantasy console doesn't actually deal in pixels, however. It deals in tiles. As we talked about before, a tile is a 32-byte data structure where each pixel is encoded in 4 bits of information, giving us 2 pixels per byte. Let's create a simple encoded tile and a function to render it to the screen. The first byte will be 0, 0, and so the first 2 pixels in our top left-hand corner will be transparent, since the transparent value is 0 in the color table. The next byte will be 1, 1, then 2, 2, and then 3, 3. That's now a whole row of pixels. And I'll actually just make the second row the same, which will give the effect of a 4x4 single color block. For the next row, we'll count up again, 4, 4, 5, 5, 6, 6, and 7, 7, and then another row of the same. We'll continue this pattern on until we've reached 32 bytes. Now we can write a drawTile function that will take an x and a y and some tile data. And of course, the x and the y here refer to pixels in the fantasy console screen space, not the canvas space. There are 2 ways of approaching this. We could loop over the 32 bytes in the tile data array and derive an x and a y pixel offset from the index, or we could use a nested for loop of x and y positions and turn that computed position into an index in the tile data. I personally find the second approach to be simpler to comprehend, so we'll use that. The outer for loop is for the y offset, going from 0 to pixels per tile, increasing by 1 each iteration. The inner loop is for the x offset, also going from 0 to pixels per tile, but this time increasing by 2 each iteration. Since we're pulling out bytes, and each byte contains 2 pixels, it's easier to just draw them both at once. To get the index into the tile data, we can take our y position and multiply it by the number of pixels in each row, which is pixels per tile. Then we can add OX to get the offset in the x direction. Of course, the tricky thing here is that we have 2 pixels per byte, and this formula assumes that each position in the array corresponds to an individual value. So we actually need to divide this answer in 2. If we only had 4 colors, and therefore 4 pixels per byte, we would divide the answer by 4 instead. We can grab the byte using our index and extract the color for the first pixel by shifting the top 4 bits down. The color of the second can be isolated by ANDing with hex F. Finally, we can make 2 calls to draw pixel, calculating our final x and y positions by adding the starting values passed into this function. Now we can draw our previously created tile at position 0, 0 and see all the colors the machine has to offer neatly laid out. Now, drawing a static tile to the screen is fine, but we actually need to be able to animate the screen, updating at a fixed frame rate. Let's add a function called draw, which will first clear out whatever was on the previous frame and draw a new one. We can clear out the frame by setting the color to white and calling context.fillRect with 0, 0 as the position and the canvas width and height. Next, we can draw the background tiles, all 420 of them. We'll render a checkerboard pattern since that's easy to compute and only needs 2 full color tiles. We can add a black tile above, which we can obtain by calling array.from with a length of 32 and setting each byte to FF. Then we can create a blue tile in the same way, this time only using 33 as the value instead. To render the background, we'll use another nested for loop, this time over the number of tiles that we have in the y and x directions. If the result of x plus y mod 2 is 0, or in other words, if it's even, we'll render a black tile. If it's odd, we'll render a blue tile. The background is static, of course, so let's add a single animated tile that changes position every frame. We can add a position object with an x and a y, both starting at 0. Every frame will add 1 to x, and then use the modulo operator to wrap back around to 0 when this tile moves off screen. We'll do the same thing with y, and then draw the tile that we defined earlier in that position. The last thing we need to do is to call requestAnimationFrame with this draw function as its callback. RequestAnimationFrame is the browser's best API for queuing up rendering-based tasks, and when the code is optimal, it can easily draw at 60 frames per second. Checking in with the browser, we can now see that we have our checkered background and a colourful tile moving across the screen, and reappearing when it goes off the end. It's not the smoothest animation in the world, but we'll be able to use a few tricks to improve the performance drastically in the next video, when we begin implementing the rest of the system. If you want to keep up with this series, consider subscribing on YouTube or join the mailing list at tinyletter.com/lowleveljavascript. And a big thank you to all of the patrons of this channel. Your support makes these videos what they are. Thanks for watching, and I'll see you next time.